Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book, a 3-volume series I wrote from 2019 to 2022. Here's pictures of each volume. The one I've been going over in this series so far is volume 1, the one on the left. This is more kind of recreational math. I think of it kind of advanced high school level math. And then volume two, the green one in the middle, that's more academic and it's probably first or second year undergraduate level and includes calculus and statistics and a lot of more advanced topics. And then volume three is problems and solutions. I have problems pertaining to each chapter of each of the first two volumes, about 20 chapters altogether, and then I have solutions to all the odd number problems. And you can purchase these series either on Amazon.com, either in Kindle or in paperback format. I do highly recommend it, and it's not that expensive. And but if you don't feel like paying the money, you could just continue watching this series. Anyway, that's my plug for the Math Lovers book. And now I'm on chapter 9, which is on dynamical systems and chaos. And one kind of subset of that topic is discrete dynamical systems, which I've been talking about for the last couple of years. And a subtopic of that is cellular automata, which I introduced in my last lesson on this feature. And if you like the subtopic, which is a big one in my opinion, is a very famous example of a cellular automata named Conway's Game of Life, which I'm pretty sure most of you are probably familiar with because it's pretty famous and there's a lot of apps available for playing it or downloading it. And anyway, must be good. So this is what my introduction to Conway's Game of Life, where I just explain what it's about. And it is an example, like I said, of a cellular automata, and it's played on a infinite square grid. I mean, in practice, it's not infinite because all computers have a finite amount of memory. If you want to simulate on a computer, it really was made for computers. Uh, Even though there's variations that involve it, you can make it finite if you want. You can make the topology either a cylinder or a torus, or you can even do more exotic topologies like Klein bottles or projective planes. But I don't want to get into that. Uh, but basically, the idea of the game of life, there's four rules. I might as well just tell you what the rules are. So there's four simple rules for this game. And like I said, it's played on a 2 by 2 grid. You have two types of cells. They're either live or dead. People have different nomenclature for this. Usually people say they're alive or they're dead. Sometimes people say they're black or white or they're off or on. It depends on your preference. But basically, there's two states of each cell. And the states evolve according to these four rules. So the first rule says that a dead cell remains dead unless it has exactly three neighbors, in which case that cell gives birth to a new cell. And then a live cell with fewer than two neighbors dies of loneliness because it needs enough neighbors to stay alive, I guess. And by the way, neighbors are every cell has 8 neighbors. The neighbors are they're kind of queen wise or king wise neighbors. They can be neighbors either vertically, horizontally, or diagonally. So just imagine 9 cells together. The center and the cell in the middle has the 8 neighbors are just all the other cells, the ones on the outside. So anyway, those are the first two rules. The third rule says similarly, if you have a live cell with too many neighbors, 4 or more, then it'll die of overcrowding. Um, yeah, I think I got rule 2 wrong. It has to have 0, 1 cells in order to die of loneliness. And then if it has 2 or 3 neighbors, it'll stay alive. So those are the only 4 rules to this game. Pretty straightforward, pretty simple rules, and it evolves according to these rules. And usually a picture is worth 1,000 words. In this case, I have little videos I've included here. This is the game of life in action, Conway's game of life in action. And it's a pretty amazingly complex game. I mean, for having four such simple rules, this is kind of how it looks. This is a typical pattern you might see in Conway's Game of Life. And you can see the areas where it's very active. I guess about half the cells here are kind of blinking back and forth. That's what's called a sort of a chaotic region of the game. It hasn't quite settled down yet. But what's interesting about it, usually these chaotic regions do settle down after a finite amount of time. And then the other stuff that's not active, you see these are called still lifes. These are some of the most common still life. I'm going to get into this in future videos, but the most common still life is called a block. That's just a 2 by 2 square made of 4 live cells. And then there's also things called beehives. Those are the ones with 6 live cells that look kind of like a hexagon. And then there's things called loaves. And there's also these oscillating patterns called blinkers, the things that are kind of the 3 cells that are blinking back and forth. And there's a lot of other kind of interesting patterns you can get. Yeah, and I think I might as well give you another interesting preview here. An open question shortly after Conway invented this game. He posted an article about this in Scientific American in 1970. I think right after he invented the game, and he didn't use a computer to simulate it. This was 1970. I don't even know if computers existed that could do this kind of animation back then. Probably not. You could play it on the computer. As a matter of fact, I did. I played the Game of Life, Conway's Game of Life, on the computer when I was in 6th or 7th grade, around 1973 or 1974. At that time, it was text graphics, and you had to wait about 30 seconds for each generation to pop up. I mean, here it's doing every generation in about maybe a tenth of a second. The generations are just the frame time between pictures here. So this is already about 300 times faster than the version I was using when I was in grade school. It wasn't until maybe around 79 or 80 that I actually saw an animation like this. I worked at a very famous science museum in San Francisco called the Exploratorium. You guys may have heard of it. It was the world's first hands-on science museum. It was founded in 1969 by Frank Oppenheimer, brother of Robert Oppenheimer. I'm sure you guys are all familiar with. He's the one who was father of the atomic bomb. Anyway, Frank was also very famous, mainly for founding the Exploratorium, the world's first hands-on science museum. I actually got to meet him a few times. I was an explainer there, so he explained a lot of stuff to us. Very, very smart man. But anyway, I'm getting kind of sidetracked here. So this particular pattern, this is a very famous pattern. This is called the Gosper gun or the Gosper glider gun. And this was the first pattern ever constructed that was proven to grow without limit. This was an open question that John Horton Conway himself asked the readers of Scientific American when he posted his article. He said, "Can you guys find a pattern that can prove grows forever?" Because, you can find a lot of patterns that seem to grow forever, at least as far as anybody could tell. There's these patterns called Methuselahs that go for a really, really long time before settling down. There's a Methuselah called the Arpentometer, where you just start with 5 live cells and it lasts over 1,000 generations, and I think it reaches a maximum population of like 5,000 or something. But the people didn't know if it was going to grow forever or not. That was an open question. But this pattern, you can see that it grows forever because it shoots off these things that are moving diagonally down into the bottom, southeast, if you like. These things are called gliders. They're actually a type of spaceship. They're moving patterns, moving oscillating patterns. They oscillate with a period of 4, and they move at what's called half the speed of light, or a quarter the speed of light diagonally down. Speed of light is just 1 cell per second. That's the fastest any influence can move in the game of life. But the point I'm trying to make here is that this glide, if you notice, this Gosper gun is shooting off a glider. It shoots off a new glider every 30 generations. That means that every 30 generations, the population grows by 5. It doesn't grow, continuously. I mean, it has a period of 30, but every 30 generations, its population is 5 larger. So that was the first pattern that was ever proved to grow without bound, to grow forever. And Gasper won, I think it was a $50 prize for finding it. And $50 was a lot of money in 1970, so I'm thinking he was pretty happy with that. You could buy a gourmet dinner at that time, even treat your girlfriend to one, I think. But anyway, so that was the first pattern that was ever proven to grow forever. And that concludes my introduction to Conway's Game of Life. And I think the next 10 or so videos are all gonna be on different aspects of this game, different types of patterns in the game. So I think this will be a fun sub series of chapter 9. Anyway, that concludes my video, my introduction to Conway's Game of Life. Thank you for watching. Long live math, and I'll see you guys next time. Bye.